So we're going to pick up where we left off yesterday in trying to define this limit. If you remember from yesterday, we had this, it was the cosine of h minus 1 problem, and we had learned that sine of theta x, or sine of theta over theta was equal to 1, right? So we learned that from this theorem 7, and that was always when theta was approaching 0. So that's the first thing we should check, is to see if it's going to 0. In this case it is. So basically I would need my sine of whatever this is, so 2x is my theta, to be equal to whatever this is down here. So that instead of having to go through my entire procedure of finding this limit, if I can get this equal to this 5x, if I can get that equal to 2x, or whatever my theta is, then I know that that would just be 1. But I can't do anything to the angle that's inside the sine. So this is sine of 2x. I can't do anything with this 2x. So I need to try and tackle how to get rid of this 5x and make that a 2x. So I can't subtract or anything fun like that. But what I can do is I can multiply both my top and bottom by 2/5. So if I multiply my top by 2/5 and multiply my bottom by 2/5, it's really like multiplying by 1, because 2/5 over 2/5 is just 1. So I'm allowed to do that because I'm doing the same thing to the top that I am to the bottom. Now by doing that, this is going to cancel our 5's out, so 2/5 times 5 is just 2. So now this becomes the limit as x approaches 0 of 2/5 sine of 2x over 2x. Now my limit laws said that I would pull the 2/5 out in front because it's a constant times the limit. So 2/5 times the limit as x approaches 0 of sine of 2x over 2x. Now because this is exactly what I'm looking for, sine theta over theta, that all just becomes 1. So my final answer is 2/5 times 1, which is just 2/5, and I showed that this limit was equal to 2/5. So anytime I see the sign of something that's other than x over something, I want to try to get this equal, or get this part here equal to whatever is in the top. By doing so, I make it so that that's just 1. This entire thing becomes 1 from theorem 7. And so my answer would just be whatever is multiplied by that. Next, we're going to look at limits at infinity. I don't know why this is all the way down here. But when I look at limits going to infinity, traditionally we've been looking at when it goes to like a point. Say the limit is x approaches 0. And that would be, if I was coming from the right-hand side, that would look like that, you know? So as I'm getting closer and closer to 0, my graph is going further and further up. Because it's going further and further up, if I was looking at it from the right, that would be going to infinity. If I was looking at it from the left, like a left-handed limit, that would be going to negative infinity. But I don't always have to look at when it's approaching a specific number. I could also look at it as the limit as x approaches infinity, Or as x goes further and further out, what is happening to this? So if I'm looking at when my x goes further and further this direction, then I can only be coming from the left going in this direction. So it'd be the limit as x approaches infinity from the left, which would be a minus sign, or from all the numbers before it. So this graph continues to go down and down and down and get closer and closer to zero coming from the left-hand side. If I'm looking at this direction, if I go towards negative infinity, going forever and ever this direction, and it's going to be going to zero as well. So that's what we're really going to get into today, because we can't just plug infinity in. So now I have to show that the limit at infinity for f of x equals 1 over x is equal to 0 as it approaches infinity, and then also as it approaches negative infinity. Yeah, write them both down, side by side. Okay. So as I'm looking at this first part here, I need to find some number, and we'll call that number m. So any number m such that for all x, where x is greater than that number m, I would need my limit to hold true, which would be f of x, absolute value of f of x, minus the limit, which is 0, has to be less than epsilon. And since I'm coming at it from the left-hand side, I'm only looking for the number that's bigger than m. So how can we find a number that's bigger than m? Well, first, 1 over x minus 0 is just 1 over x. And then if I get rid of my absolute values, then that's just going to give me 1 over x. And since I'm only coming at it from the one direction, it's less than epsilon. Now, because x is in the denominator, flip this, and I flip this one, so that I get x over 1, which is just x, is greater than 1 over epsilon. Remember, this is epsilon over 1. Anytime it's a whole number, it's over 1. So I need to have an x that's greater than 1 over epsilon. In this first half, by the way, your inequality flips whenever you flip something. So by flipping this and making it x over 1 and this 1 over epsilon, that's why this became a greater than symbol. So now this looks exactly like this, and so I know m equals 1 over epsilon. So I can find a number for m so that everything would fall within this range, which proves that the limit is equal to 0. If we look back at what our graph of our function looked like, and I'm going to drag it over to here. If I pick some random epsilon that it has to be within 0 on, say here, actually we'll go right to 1. So if I pick some epsilon of 1, then my number, so it has to be within epsilon of 0, then my number for the x that I would come up with, which would be 1 over epsilon, have epsilon equal to 1, 1 over 1 is 1. This value from here on is less than 1. Or I mean, is greater than 1. So as I look at my epsilon, from here on out, everything greater than 1, as my x gets greater than 1, is getting closer and closer to 0. So it's all within inside this range for my y. If I wanted to set my epsilon to being 2 units away from 0, then my delta would have to be 1 over epsilon, which is 1 over 2. If I look here, from 1/2 on, it's lower than this y value. And that would work for every epsilon value I chose. No matter how far away from 0 I get, it's going to keep doing the same thing. So that works exactly the same way when I'm going the opposite direction. As I'm going towards negative infinity, it does the same thing. I would then need to choose a n, we'll say, or just some number, and then my x would have to be less than that. So if I pick some random number here, call that n, then I'm saying for every x that's smaller than this, or as I go more and more negative than that, I can find an epsilon that's going to be small enough to make my delta work. So it's the same equation, 1 over x minus 0 has to be less than epsilon. And then it's going to end up at the same place, absolute value of 1 over x less than epsilon. Since I'm coming from the negative numbers, when I get rid of my absolute value, it's going to be 1 over x less than negative epsilon. Over here it was positive because we were dealing with all the positive values. Because my y was always above the x-axis. Here it's always below it, so it's always going to be the negative epsilon that I'm dealing with. And I come up with the same thing. So you would flip it, it would be x has to be greater than 1 over negative epsilon or negative 1 over epsilon. That actually, when I made this negative epsilon, this has to flip to a greater than, and then when I flip it, it flips back to a less than. Sorry. And so all that just proved that 1 over x, the limit is x approaches negative infinity, and the limit is x approaches infinity of 1 over x is 0. Now that we know that to be true, then anything that's smaller than that would also equal 0. So all of our limit laws that we learned apply to this as well whenever x is positive and negative infinity. And I will let you write all of this greatness down, because this is theorem 8, which is just our limit laws as x approaches positive and negative infinity. So if I have that f of x equals L as x goes to positive and negative infinity, then as x goes to positive and negative infinity of g of x, that gives me the limit of m. Then the sum rule says if I'm taking the limit of both of those combined, added together, it would just be the limit of the first plus the limit of the second. Same thing for differences. If I have the limit of the first equation minus the second equation, then I do the limit of the first, which is L, minus the limit of the second. Product rule works exactly the same. Constant multiple rule, quotient rule, and power rule. So now if we use theorem 8, or what we just learned, what that means is I'm going to break each one of these up. Instead of combining the two of them and trying to figure out what 5 plus 1 over x is, the limit laws tell me that I can take the limit as x approaches infinity of 5 plus the limit as x approaches infinity of 1 over x. So by breaking those two up, I have a good idea of what this is going to be. There is no x in this first portion, so it doesn't change at all. It's always just 5. So the first part of this is 5. And then what is the limit as x approaches infinity of 1 over x? We just learned that to be 0. So instead of trying to deal with this all at once, I know that it's 5 plus 0 by breaking it down, and my limit is just 5. So by breaking this problem up, we can fix it. So it's easy. This problem looks brutal. It's the limit as x approaches negative infinity of pi times the square root of 3 over x squared. Well, this top part, even though it doesn't look like it, it's just a constant, right? Because pi isn't a variable. It doesn't change at all. It's always 3.14. Square root of 3 is always 1 point something. So that's just a constant. So the constant multiple limit law, so that I can pull that out in front, it's pi root 3 times the limit as x approaches negative infinity of 1 over x squared. So when I look at this, this looks a little simpler, but not really, because I don't know what 1 over x squared is. I don't know what that limit is. But 1 over x squared is really the same as 1 over x times 1 over x. So now I have pi times the square root of 3. Limit as x approaches infinity of 1 over x. And that's times the limit as x approaches infinity. I'm sorry, these are negative infinities of 1 over x. What is the limit as x approaches negative infinity of 1 over x? That would be 0. So that's times 0 times 0. Pi root 3 times 0. Anything times 0 is just going to be 0. That is our limit. Any questions on that? We just learned here that the limit as x approaches infinity of 1 over x equals 0. So since I know that, I got to memorize that now. And then here, the limit as x approaches infinity of 1 over x was 0. Because I knew that from the last problem. Same thing down here. By seeing this 1 over x squared, I can break that up because it's 1 over x times 1 over x. Break that up into two separate limits. Since I know that this is equal to 0, it makes it easy for me to solve. Since I know this is 0, that became a 0, and so did this one. So the whole thing turned into a 0. All right. Okay, so for tonight, I'll give you some homework. I'm looking at a quiz on probably Monday on the first 4 sections of this chapter. I might make it Tuesday. I'll look at it tomorrow and decide.